welcome to Engineering with Rosie Live. As always, please let me know in the comments that you can see and hear all of us here, because sometimes I make a mistake and you can't, and then that's very awkward if I just talk to myself for a while. Okay, so in today's live stream, we're going to be talking about space for climate change, which is only kind of tangentially related to my latest video, which was on how to power a human Mars mission, but it is somewhat related at least. And we have three amazing guests today who I'm going to introduce to a second, but you can just say hi now. Thank you. But first, in the comments, can you please tell me where you're listening in from, and tell me how many of you wanted to be an astronaut when you were growing up? So I asked that question because I did want to be an astronaut when I was growing up, and I went as far as doing 1 year of my engineering degree in America at UC Davis, and I studied all of the core aerospace engineering subjects in that year, including actually we had a senior design project, a group project where we all actually designed a manned mission to Mars. So I kind of had forgotten about that till I made a video on that topic. So while I was there studying that, I decided the space is super, super cool, the coolest probably. I mean, I still think that, but I also felt like we have a lot of problems on Earth that I wanted to help solve. So I moved into renewable energy, but I do still want to be an astronaut. And I reckon, we're close enough now. Space tourism is like, surely I'm going to have a chance to be a space tourist at some point in my life if I want. But it feels like a pretty frivolous way to use up the carbon budget that we have, to prevent catastrophic climate change. And I think that that's an opinion that a lot of climate concerned people have. So I was asking, is all of the space industry just an emissions intensive ego boost for billionaires like Elon Musk and Jeff Bezos? So to answer that question, I got in touch with my friend from during our PhD days, Courtney. We were together at UNSW. She was working on cool space stuff, and I was working on a wind turbine project. And then she introduced me to another couple of people who can help with this topic. So I will take this opportunity to thank and welcome our guest today. We've got Courtney Bright. She's a space systems engineer at CSIRO, which is Australia's science organisation. She does spacecraft system design, testing and operations, translating science and end user needs to feasible engineering requirements. Then we have Jasmine Muir, who's a senior consultant at Symbios Space. Is that how you say it? Am I saying that wrong? She has extensive experience across government, academia and private industry in developing satellite Earth observation solutions to deliver sustainable outcomes in the agriculture and mining industries. Those are two topics that I am super interested to talk about today. And then lastly, George Dyke, who's also a consultant in Symbios Space, and he works on Earth observation satellite applications, satellite systems performance and plans, and space robotics. And I know that you are used to talking a lot about space. So I will give you each a chance to say something about yourself before moving into the content. But before I get to that, I do have to thank the sponsor of these live streams, which is WeatherGuard Lightning Tech. They make strike tape, which is a retrofittable lightning protection system for things that go fast, like wind turbine blades and aircraft, but not as far as I know spaceships. I assume you wouldn't launch if there was lightning in the area, but maybe that's a question that one of you guys can answer for me. But anyway, these live streams wouldn't happen without their support. And then also the whole Engineering with Rosie channel is sponsored by the amazing Patreon community. So yeah, first of all, can someone tell me what happens if there's lightning during a launch of a satellite or a space shuttle or whatever? Do they have lightning protection, or do they just not launch? Or if I throw in your completely curly question that no one knows the answer to?
That's a really good question that I've not thought about. Go ahead. You sound like you might have a more confident answer.
It's generally a no-go for launch, sort of like with aircraft, same thing. But when you look at a launch tower, like a Cape Canaveral or something, you'll see giant poles all around, usually 1, 2, 3, or 4 of them, and those are literally lightning rods to try and, I guess, attract the lightning away from the rather large fuel mast sitting on the launch pad. But no, they wouldn't necessarily launch. It's funny though, because once they get into the atmosphere, there's, all bets are off. Lightning is everywhere. So, yeah.
Yeah. Right. Okay. Huh. Okay. So anyway, I've distracted us from my main job today is to keep everything focused, and I have just immediately started by going off on an unrelated tangent. Yeah, so I hope this is going to go well with so many guests. It's the most that we've had before, but I think it would be good if we could spend just a quick second for each of you to say something about yourself and why you're interested in this topic without taking up the whole hour talking about that. So can we start with Jasmine, maybe?
Thanks, Rosie. So you were talking about wanting to be an astronaut. I actually got into this area because I wanted to look back down on Earth and help us with some of these environmental sustainability questions. So that's why I've ended up studying Earth observation. I came in from an ecological background, so that's my undergrad training. And really interested in those environmental sustainability aspects.
Yeah, cool. How about you, Courtney? I know you didn't want to be an astronaut when you started.
No, I didn't want to be an astronaut mainly because I like fresh air and trees, and being cooped up in a space station doesn't really do it for me. But yeah, space kind of got me into science and physics, which led to engineering, did a mechanical engineering degree. And then when I finished that, I kind of cared about the bigger picture of what I was working on. I wanted to work on either renewable energy or space exploration. And yeah, ended up going down the space route, doing a PhD in that, working in satellite operations for a few years. And then over that time, kind of the environmental aspects started to become more urgent to me. So I tried to find a way to combine the space experience, but on environmental applications. So that I moved to CSIRO and now focus mainly on Earth observation projects.
Yeah, cool. And how about you, George? How'd you get started?
Yeah, I was just thinking about lightning still, but yeah. So I did mathematics and mechanical engineering at university, and that led me to the space community. I worked on the Canadarm2 program on the International Space Station in Canada, and then for the last almost 20 years now, I've been involved in Earth observation. So a bit like Jasmine said, sort of turning the camera back onto the Earth, and I think there's a lot of really interesting and important big challenges there. So that's how I got into it. We've followed applications of satellites from all different angles, but climate has been one of the major threads, and satellites are really highly relevant to climate science, especially, and increasingly action on climate. So I think this is a really interesting session. And just picking back up on lightning, so just in the last few years, one of the most interesting new sensor types is a lightning detector, which can detect lightning from space, from low Earth orbit and now geostationary orbit. And it can give us an unprecedented picture of lightning strikes in the whole Earth hemisphere, basically updated every tens of seconds, which is an amazing new capability. And there is a lot of lightning out there. So, yeah.
Yeah, oh, that's interesting. Lightning is super relevant for wind in my work, my real job that I do. It's a lot about failures in wind turbine blades, and lightning is a big cause of fights between wind turbine owners and the manufacturers and the insurance companies. None of them ever want to take responsibility. I do just have to show this funny comment before we move on from Will Burke. It says, actually, for satellites, lightning is good and lightning is bad, because another commenter made a spelling mistake and said lightning with an E in it, which is obviously making something more lightweight. So nice pun. Will appreciate that. Okay, cool. So let's move on now to the main thing, why satellites are useful and about how they're used for Earth observation. So I think, Courtney, you wanted to take this.
Sure. Have you got, there's a good slide. The first one with graphs. Yeah, that one.
This one?
Yeah.
Okay, cool.
So I kind of went through a lot of satellite databases trying to learn a lot about this myself as well. And there are about 5,500 operational satellites at the moment, although that is a May 2022 latest update. I think since then there's been about another 1,500 satellites launched, which has been largely SpaceX's Starlink constellation. But so of all the satellites that are operating at the moment, most of them are for communications. And you can see I've kind of split here civil, commercial, government, and military. So by far the biggest chunk of satellites operating at the moment are commercial communications satellites, and most of those are Starlinks. About 21% of all of the satellites at the moment are for Earth observation, which I guess we'll spend the rest of this live stream going into. Quite a few for technology development, navigation and positioning, so all our GPS satellites, space science, so those tend to be the ones that are looking back out at space, and other things that don't fit into the other categories. Of all of this, so Earth observation, we've got a good chunk of commercial, so that's things like our Planet Dove satellites, government, which is kind of our bigger either Earth mapping or science missions by, for example, European Space Agency or United States Geological Survey or NASA, various other countries as well with satellites, or military, and there you're kind of looking at obvious military looking down at Earth applications, but also things like shipping and aircraft detection. Yeah, you can probably move on to the next slide unless you've got any more questions on that. So all of those, we've got them split across different orbits. So by far, sorry, this is Earth observation satellites. So again, from all the ones that were operating in May 2022, most of them are in low Earth orbit, which is kind of between 200 and 2,000 kilometers altitude. For those ones, you've got them doing essentially laps of the globe, about doing one lap every 90 minutes or kind of 15 laps a day, slowly building up a picture of Earth. Having said that, they might be always kind of pointing straight down and building up a global map, or there might be more targeted pointing missions where you've got particular sites that you're interested in that you're pointing at. Geosynchronous orbit is, I guess, the next most common, or geostationary orbit, which is where we've got them at a certain altitude far higher than the low Earth orbit, and that the period of the orbit is the same as the period of Earth's rotation. So you end up looking at the same spot on Earth, and you end up with you can see about a third of the Earth from that altitude. So you end up fixed over that point, continuously gathering information. And that's particularly useful for weather satellites. And then we've also got a few in a highly elliptical orbit, which can be quite useful for remote sensing over the poles. Then I also had a look at the distribution of how big are all these different Earth observation satellites. So they're fairly evenly distributed. We've got quite a lot, particularly recently, around the less than 10 kilo range. So examples of that are the Planet Dove satellites, which are about the size of a loaf of bread, all the way up to over a ton. And then you're looking at your big global mapping missions, things like the Landsat and Sentinel missions, which are about 2.5 tons each, maybe the size of a minibus. And the biggest one we ever had was NVSat, which is not working anymore, but that was 8 tons and about the size of a bus with a huge 15-meter solar array on it as well. So we're kind of, we're going from very small to very large. And they'll all have...
I actually had no idea that satellites got that big. I was imagining them all, like a, I don't know, cardboard box size sort of thing. But there you go. I'm learning something.
Cool. What have I got on the next slide? Okay. All right. So of those Earth observation satellites, I wanted to do a nice graph categorizing the applications of each of them, but when you look at the databases, the application will be kind of a paragraph for each satellite. So instead did a word cloud from one of the Earth observation satellite databases. So this kind of gives you an idea of the most common things that they end up being used for. One satellite is often used for multiple environmental applications, but environmental monitoring is a big one. Climate data is a big one. Land cover mapping, ice mapping, sea surface temperature, sea surface level, and so on. Agriculture is another one that Jasmine's done a lot of work in, so I can probably speak to a little bit more. So this is kind of just a an overview, and we can dive into some of these a little bit more over the next 45 minutes.
Let's keep pushing through, because I know we've got way more to talk about than we'll have time to get to. So is this still on that same section?
Yeah, we can skip over this. This was more if questions came up. But okay. Yeah. So these were all just examples of the different ones in here. So another one I didn't mention is weather forecasting. This one here is an example of how the how satellite data impacts 24-hour weather forecast accuracy. So essentially, the bigger the bar here, the more it impacts the forecast accuracy. And I've just put a little satellite next to all of the different ones that come from satellites. So the top 3 contributions to weather forecasting accuracy all come from satellite data.
Yeah, right. I mean, that's obviously super relevant to the energy transition because, wind and solar power are variable, but if you can predict the weather, then obviously then they're predictable. So that's interesting to know. Because, I mean, I read somewhere that the accuracy of week ahead forecast now is around the same as what 2 days ahead used to be a couple of decades ago, and I guess that satellites is a big reason for that based on what we can see in that chart.
Yeah, George has added in another good plot, which I think is the next one, which shows, George, do you want to speak to this one?
Yeah, it sort of makes the point Rosie just did, which is, satellites are a huge contributor to the accuracy of short-term weather forecasts, so up to sort of 10 days. And I think that impacts the whole global economy. It's much more than just, is it going to rain for my picnic? It's, global shipping, aviation, anything operational depends on, accurate weather forecasts, and satellites have been hugely influential, especially in the Southern Hemisphere. So, and I don't mean that because we're based in Australia, but if you chop the world off at the equator, most of the land is in the Northern Hemisphere. And so most of the land-based observations that go into weather are in the Northern Hemisphere. So satellites really increased the observational density in the Southern Hemisphere a huge amount, which reduced a lot of uncertainty in the weather models. Without that, we wouldn't have physical observations. Or at least we'd have a lot less physical observations. So
that's interesting. I think the next slide is still about forecasting.
Yeah, you can keep skipping.
Okay. What's this one?
If you feel like going into a picture, there's a good, if you go to the link, there's a good video, but I don't know how technically difficult that is to do during the live stream.
I can achieve it, but not right this second. So,
okay. So this is kind of a screenshot of a video where you've got the 4 Sentinel and Landsat satellites kind of slowly, and these are in low Earth orbit, but building up a picture over Earth. And we were kind of wanted to use this to illustrate, I guess, the advantages of satellite. One of the advantages of satellite data over ground-based measurements, for example. So you're able to build up a global picture with a much smaller number of sensors. So, for example, looking at this picture of the globe, Landsat, there is 30-meter spatial resolution. So to cover the entire Earth with sensors every 30 meters is not viable. And you would also have different calibration for all those different sensors. This also allows us to build up a kind of consistent time series over a number of decades, which is particularly important for things like environmental monitoring and the climate record. George, do you want to add anything to that?
Yeah, I think you've covered it really well. The global consistency is really key. So in this case, we have a satellite going around, and the key point for me is that it's the same instrument measuring the entire globe. So if you have a in situ or like a measurement site on the ground, like you said, Courtney, you've got, maybe hundreds of those kind of observations, and they all have slightly different calibrations, and it might be a little hot at one site and a little cold at the other site. So whereas this is a consistent observational baseline, and it keeps happening. As you said in the intro, these satellites go around the Earth 14 and a half times a day, every day. And so you're really building up a huge baseline of knowledge and information.
I love that
And also
animation. That's really cool. It's like hypnotic.
it also lets us access sites that would be very difficult to access remotely. And there are some downsides we need to deal with cloud cover for optical satellites, for example. So you might go over a certain bit of land, but you've got clouds, so you can't get anything useful out of it. So you lose maybe half of your imagery that way for optical instruments. And spatial resolution is a downside. You are relatively far away. So compared to flying a drone over a site, for example, your spatial resolution is relatively low. So ideally you have kind of a network of ground-based sensors that are satellite data that's complemented with ground-based sensors, so that you're covering essentially everything you need.
Okay, cool. So that's a lot about the what of satellites, which is good for me or someone like me, probably most of my viewers as well, who aren't super familiar with what satellites are like and kind of the limitations. Because I know, I hear about all sorts of things that are being measured with satellites, and it's kind of hard to form a view of how that actually happens. But I'm pretty keen to spend a lot of time talking about what we're doing with that, with those satellites. So we'll move on then. Yeah, and sorry, I can't remember who was the next person who was going to talk about that.
George.
Okay.
Yeah, so I see there's a few good questions in the chat, which is great, and I think we'll get to one of them on sea level measurements in just a couple of minutes. But I guess, so we've talked a bit about technology, the whys and all that, but there's a few really good examples, I think, that bring this stuff forward. So weather is one. Weather forecasting is clear public good. If you look at something like the ozone hole, which was detected, between the mid 70s and mid 80s from the ground by the British Antarctic Survey, once we got satellite images of that hole, it became really clear the scope and scale of the hole. It wasn't just a point above a ground site. It was a huge gaping gash in the atmosphere. And that really motivated public action. And so we had the 1987 Montreal Protocol, which was created under the United Nations framework. It limited the use of harmful refrigerants and accelerants, so things that make your refrigerator or your spray can work. And since then, satellites have been monitoring the regrowth of the ozone hole and provide us with a great time series record. And I think the 10th slide of that slide deck shows a bit of that. But basically, it's been able to show that our actions as humans have started to reduce the hole in the ozone layer. And it looks like by 2040, if we keep on this path, we will basically recover that hole in the ozone layer. And without satellites, these sort of curly green-blue figures on the screen wouldn't really exist. So these observations are showing us that the Montreal Protocol is working and the ozone layer is, I guess, healing up. And so I think this is a really interesting and powerful example. These satellites were built by space agencies all around the world. So in Europe, the US, Canada, Japan, and other countries. So there's an ability for transparency. If a country doesn't believe that something's happening, they can use this technology to have a look and check on what's going on. So it's a really powerful story, and I think we're going to be able to see a day when the ozone layer is healed. So I think that's a really, I guess, powerful example of what's possible. There was a question about sea level rise, and it was actually specifically about accuracy, which is a super good question. But sea level is another variable. And this is a major variable in the climate system that's measured from space at an unbelievable level of accuracy, considering you're hundreds and hundreds of kilometers above the surface. You can measure down towards millimeter level accuracy. And if you put up slide 12 there, Rosie, it shows a graph of, I guess, the history of sea level rise back to 1880. And this is maintained. The sort of bluer bit towards the left is, ground-based records from jetties and coastal observations. And those are still going on, still very important. But on the right is the last sort of 20 years or so where we've had really high-quality satellite data. And not only does it give us amazing accuracy, but it tells us the spatial distribution. So different parts of the ocean have experienced sea level rise at different rates. And some of that's based on the temperature of the ocean, some of that's based on prevailing winds. And so from satellites, we can collect a really detailed set of information about the ocean surface, to the point where when you're looking at La Nina or El Nino, one of the early signals for that is actually sea surface, sea level. So we measure temperature from space, but also because the ocean water expands, the sea level changes, and we can measure La Nina and El Nino from space. So that's quite a high level of detail.
Yeah. So is that something that El Nino and La Nina are super important in Australia? Because, it's either we've got droughts and bushfires in El Nino year, and we've just had 3 La Ninas. Wait, am I got that back to front? One way around or the other. We've just had 3 back-to-back wet years and heaps of flooding. But is it only Australia that suffers from this? Or, that's a Pacific Ocean thing. So presumably some of the west coast of the Americas would suffer and Europe wouldn't care at all. Is that about right?
Well, maybe Jazz or Courtney knows better, but California is sort of the inverse experience of Australia. So when it's wet here, it's dry there, and one of the major correlations is El Nino, La Nina. And it's also, like weather, climate is a global phenomenon. So nothing is really actually disconnected in that way. The oceans are one of the major heat pumps of the world. The oceans move heat around the world more than anything else. And so when you have a huge heat fluctuation in the Pacific Ocean, that heat's getting pumped straight down to Antarctica, which starts to melt glaciers, and then that cools and then goes up in the Indian Ocean and affects weather in India. So it's pretty globally integrated. It is directly, yes, Australia, California, the Americas mostly impacted, but it is a globally important variable for climate.
Okay.
And there are other such things.
Yeah. All right. I think this is relevant to what we're talking about, and to the next slide you have. Jim Murata asks, how have the instrumentation and sensors on board satellites advanced recently? And so I saw this timeline of radar altimetry missions, and presumably there's some kind of technology story that's happening there with the different things that have happened recently compared to what happened in the past. Is that something that you can talk about, George?
Sure. So this is actually, yes, a figure of the sort of family of sea surface measuring satellites over time. And these to date have been what's called radar altimeters, and they give you a point observation of, maybe not a single point, but a small dot of sea level. If you look, there's an instrument called SWOT, S-W-O-T, and it just launched late last year, and it's actually going to give us a swath of altimetry. So instead of a point, it's more like a line of elevations. And it's going to enable, we can fill in gaps in the current observations. So where we had points, now we have a line, so continuous global coverage. It's improved the resolution, and one key outcome of that is we'll be able to measure inland waters and river systems using these technologies. So previously, this has been a sea level measurement, But if we can, say, make an inventory of the global river levels, using satellite radar and the fluctuations there, then that's a new piece of knowledge. We have in situ observations for that, but this global picture of, how are the various river levels in the world changing, or large lakes. And we can't get down to puddles and, that level of resolution, but I guess in this space, new observations around inland waters are really interesting and should tell us some new things about the water cycle and impacts on it.
Okay, cool. It's amazing what you can what you can achieve with something so far away to be able to make such precise measurements. I would love to actually, talk for hours just about the technology of satellites, not just with respect to sea level rise, but, all the things that they can measure. But I think we better keep pushing on. And I think the next topic is to do with monitoring emissions and that sort of thing. And I write that. Oh, it's also, George, and I think Jasmine was going to talk a bit about that as well.
Yeah, I'd like to be really brief, and I'd like to hear a bit of Jazz's experience with the deforestation and agriculture side of things. But continuing on a theme, we have long records from the satellite era, I should say, of greenhouse gas concentrations going back to the 80s. And the capability there has gotten better and better. At the beginning, we were looking at continent scale, country scale kind of observations, and now we can really measure emissions like CO2 and methane down to a facility level. And so we're starting to get to a place where we could be having a look at factories or power plants or mining companies, infrastructure or landfills is another big emitter of methane, and trying to call attention to places that need things to be done. And one of those is definitely forestry and deforestation. It's a very key, critical carbon sink and source, unfortunately. So
and it also feels like, I'm really interested in all these kind of measurements because it feels like it's finally a way to, you don't have to just take someone's word for it, So in the past, like I've always been super skeptical of some of the kinds of carbon credits you can buy because it's like, oh yeah, we paid a farmer in Zimbabwe to not cut down a tree that he promised us he was going to cut down otherwise. Always seemed super dodgy. And then, with satellite monitoring, you can check that. And I think that Jazz is going to talk more about that specifically. But I wanted to ask, maybe it's a dumb question, but I don't know. How on earth do you how can a satellite measure a carbon dioxide concentration or a methane leak or anything like that, especially at such a precise level? Is that something that you can answer, or have I asked a really difficult question?
It's neither difficult nor dumb. I'm sorry, it's neither dumb, but is very difficult, I should say. Okay. Look, I'm not an instrument scientist on this stuff, but what you're measuring is generally columns. So a column density of CO2. And what I mean by that is the whole atmospheric column from top to bottom, you're getting a one number for it. There are ways that you can measure, get a sounding, which is more of like a graph at different altitude levels. And all of that has to do with the absorption spectra of different molecules in the atmosphere. So, different molecules absorb different wavelengths of light, so you know what you're collecting, and you can map it to particular gas or particular gas, basically. But that's almost the end of my understanding in terms of how it works. So.
Yeah, if anybody else knows more than that, jump in, but I won't make you try and explain something that you're not used to talking about because I know how hard that is.
That's a good graph, by the way, this fingerprint here that you've put up. It's exactly the kind of thing. So you have bumps at different points in the spectrum and they correlate to different gases.
Yeah, I can jump into this a little bit more, this example is one from NASA JPL's EMIT mission, which is on the International Space Station at the moment. And it's detecting methane. That wasn't actually its primary mission, but it happens to be able to do that as well. And it's detected something like over 50 super emitters from methane point sources, and just in kind of the commissioning phase of its mission. But here's an example where it's an imaging spectrometer. So for each pixel in this, the front, like the visual part of the square there, for each pixel you end up with a spectrum of the light that's reflected back from the surface, and depending on the shape of that spectrum you can identify individual minerals, for example, different constituents of the atmosphere. Depending on the specifications of the sensor, you can identify things like what plant species you're looking at, or whether the plant is under stress, and so on. On the next slide there's a cool example of, well, it's just a big methane plume, and I think this one was over Turkmenistan, and this was over a bunch of coal and gas infrastructure there, and I think it was emitting something like 50 tons of methane an hour, which was kind of around the same order of magnitude as the biggest methane leak that had ever been recorded in the US. And yeah, this wasn't its primary mission. A similar sensor is going on to a constellation of planet satellites, which will be called the Carbon Mapper missions. So I think the first couple of those are launched later this year. And yeah, there's a bunch of other spacecraft doing similar things, but at different sensitivities and spatial resolutions, where we should be able to build up a good global picture of what's happening with different methane emissions and CO2 emissions as well.
Okay, and that's from that same.
Yeah, a lot of these missions as well are really moving toward open source data. So we'll put the link in the chat for this one, but you can go in and have a look at all the different methane plumes that have been detected from the EMIT sensor, for example, and Carbon Mapper is the same. All of that data will be open source, as well as most of the other greenhouse gas monitoring satellite missions.
Okay, cool. I'll try and I'll put all of these links in the description afterwards, and see if there is some way that I can add these slides as well. Although I guess you can get them on the replay. Okay, we just had a comment. Is there any data on the methane leaked from the Nord Stream bombing? And I guess I could generalize that by saying, yeah, how can we see where these methane leaks are? And one thing that I've noticed in the news is it seems like every few months we find out that methane leaks are worse than we expected from things like coal mining and gas as well, and pipelines and that sort of thing. Are those sorts of events? I assume that's monitoring that's come from satellites, right? And is that covered in the same open access data sources?
That's an interesting one. I mean, so there were certainly observations of the Nord Stream, which is a giant plume of methane coming out of the middle of the ocean because of ruptured something underwater. Sorry. But what's interesting, Rosie, about what you said is there's not really. There are global observations, but making the inventory of what's been emitted is more of a national level function. I mean, scientists do that in the name of science, but countries are sort of responsible for accounting for their own emissions. And so that's really something that a national government would do. But in this case, it's obvious satellites can be used to sort of expose areas where there's a lot of emissions, and we're working on, I guess, a more rigorous connection between observations and making, let's say, someone take an action like stopping the methane flow. With methane, usually, like you said, it's a lot of mining, so and extractive industries, gas and oil, and they do have an economic interest often in limiting this, whether it's because they're outside of regulatory boundaries or whether it's because the gas is their inventory and they don't want to be leaking it. So I think there's a nice value alignment there that will develop in the next few years.
Yeah. Okay. Yeah, it just seems like the problem gets bigger and bigger all the time, all this methane problem. And there was another interesting comment about methane, which I'll read, but I don't want to talk about it now because we're running out of time to talk about the other topics that I want to cover. So John Norris says, I've heard that a large portion of the methane being added to the atmosphere is from livestock, which is worth oil production or animals. And yeah, I don't know the answer off the top of my head. Very interesting point for later. If one of you knows the answer in just a one-word answer, then feel free to chime in. But otherwise,
have a look at the International Methanes Observing Initiative, IMEO, I think it is. They have answers to those kind of questions.
Yeah. Okay. Well, maybe one of our viewers can look that up now and write the answer in the comments. But I am super keen to talk about deforestation, and we haven't got a whole ton of time left. So I think, Jasmine, that was one that you were going to talk about some of the work that you're doing there, right? And that also you work with agriculture as well, so maybe you can talk a little bit about that as well if you feel like it.
Yeah, thanks, Rosie. So one of the great things about working with satellite imagery is the ability to look back in time. And missions like Landsat, which Courtney was talking about earlier, that gives us 50 years of land cover history. So we can look at how the forests have changed in the past 50 years. And if you think about areas like the Amazon, that allows us to see exactly where deforestation has occurred. But not just the Amazon. There's been a large amount of land clearing that's happened in most countries around the world, and we're able to monitor that with satellites. One of the questions earlier was how have instrumentation and sensors on board satellites advanced recently? So things like spatial resolution. Landsat itself was originally about, I think it was a 50-meter resolution. It's now currently a 30-meter resolution, but we now have satellites that can get down to 2 or 3 meters and are covering the Earth daily. So the planet satellites, they're at that fairly high spatial resolution. So we can now look at how things are changing on a very small cadence, and we're able to detect events almost immediately after they happen. In Australia, we have a few different monitoring programs that do look at land deforestation. One of them I used to work for in Queensland in the government there. It's called the Statewide Land and Tree Survey, and they monitor all of the land clearing that happens in that state on an annual basis. A lot of it in Queensland is related to various different agricultural practices or monitoring forest fires, things like that. So I guess what I'm trying to say there is not all of the deforestation that we might detect is related to human-induced activities. It can be related to things like forest fires as well. Just also with deforestation, I think we talked briefly about carbon credits. Carbon credits are definitely things that can be monitored using satellite imagery. There was recently a interesting story about monitoring in Papua New Guinea of some of the carbon credits that have been purchased by some quite large companies here in Australia. And better monitoring using satellite imagery would be able to tell us exactly what's happening there on the ground. So having that knowledge across large areas on the ground is really where we want to see satellites being used and where they can give us the most utility. So that's really
before we move on, can I
quick...
ask a question about deforestation? Because I know, I don't know, but when people talk about deforestation, they're often talking about, like in Indonesia and palm oil plantations, and also in the Amazon and maybe some other less wealthy countries. But I worry a lot about deforestation in Australia. I know there's not so many countries as wealthy as Australia that are still chopping down their native forests as quickly as us. And I did read something in the news recently that improved satellite monitoring was allowing them to figure out that some logging activities were maybe being performed illegally. I think it was something to do with the amount of trees that have to be left in an area to count as being, a forested area, and maybe there was a lot of thinning that was happening. And sorry, I'm saying this really badly, unclearly, but the point was that the threshold for tree cover was based on what they used to be able to, the resolution they used to be able to get at with satellites, and now with improved monitoring, they can see actually a lot of trees are being cut down in areas that, for the purposes of carbon accounting, it's assumed that it's fully forested area, but actually they've cut down a third or 2/3 of the trees there. The carbon accounting makes no difference, but of course the atmosphere does care if there's 1/3 the number of trees that there used to be. Is there a lot going on even in like wealthy countries like Australia, satellites helping us to get our act together as well? Do you see change there, or do you think there will be change in policies and the carbon accounting methods as a result of improved satellites?
I think that's quite a big question, and I'm not sure we've got time to go into all the detail behind that. But the piece I'd like to talk about is definitely spatial resolution does play a role in what we can detect on the ground, and you really need to be quite cognizant of the data that you're using to be able to correctly interpret it. So I think Australia's got very good capabilities in that area, and we're able to use that information effectively.
Yeah, okay. I hope that, I really would love to see no native forest clearing, especially in Australia. That's one of my big motivators for working on climate changes, because I really love the environment, and I love the animals that live in it, and it makes me really sad. And I'm happy that we're improving the tools to deal with that now. But okay, we can't talk about deforestation all day. So was there anything else that you wanted to get into, Jasmine?
The other thing I was just going to briefly touch on is how we can use satellite imagery in agriculture. So a lot of imagery can be used to look at helping to improve farm management practices, but it's also really effective at reporting statistics across large areas. So one of the projects I was involved in last year was working with FAO and reporting the crops that are produced in Africa. So that allows organisations to understand what is the availability of food and what's the likelihood of things like impact of drought on countries' populations. So I think that's a really important part of using satellite observations to help understand how people's lives are going to be affected.
Mm. And can you get down to really like specific agricultural things? Like, can you zoom in on one farm and see what's happening there, or is it more of a an area wide type observation?
That's a good question. And with some of the modern satellite sensors we have up there, yes, you can get down and have a look at what has been planted on one particular farm. It's certainly easier in places like Australia, where we have very big fields that our crops are growing in. When you go to areas such as Africa, you get very small fields that are still quite difficult to see from even a 1 meter or 2 meter satellite image. But you can get down to that individual farm level, and you can use the data on farm to help with your management. But also that reporting at the more regional level, that's really important for things such as knowing what's happening across a region or a country and feeding into policy.
And we've got a comment from Click saying drones do better farm management. How do you see those two working together? Are they duplicating the same types of measurements, or they're working together? Are there things satellites can do drones can't? And obviously vice versa, that would be true.
Yeah, definitely. Drones are probably more suited to that farm scale management, whereas satellite imagery is more suitable for the regional scale, looking at what's happening. There's certain aspects of each that make them more advantageous. You don't have to go out and fly a satellite. It's already there collecting the data for you, whereas a drone, you still do need a trained pilot to be able to collect that information.
Yeah, okay. I guess that's another thing where the large farms in Australia make it more likely that you would bother to invest in those capabilities.
That's right.
Yeah. Okay. I think we've got time for a brief covering of a big topic now. This is one that I don't know. I'm super interested in the deforestation and methane monitoring, but also the last topic is on the carbon footprint of a satellite mission, because I think, I'm keenly watching how these things can kind of, space can get greener, because I do still hold that hope that one day I can be a space tourist without too much hypocrisy. So I guess we'll clean up the satellites first and then the spaceships. But I think, Courtney, you were going to talk a bit about what the carbon footprint of a satellite mission is.
Yeah, if you could bring back the slides again, I've got some plots. But in the meantime, I thought this was going to be a really quick Google, what is the carbon footprint of the space industry, and it turned out to be a lot more complex than I thought, with a whole lot of rabbit holes to go down. So I'm going to try and keep this very, very quick, but it's a big topic. I wanted to maybe start just by putting it into perspective. So to give an idea, one launch of a Falcon 9, which I think was the most common launch vehicle last year, is equal to 237 Sydney to London flights on a Boeing 747, which sounds like a lot.
You mean the whole flight, not like 237 passengers, but 237 plane loads.
Yeah.
Okay.
And that sounds like a lot, but it turns out, in the grand scheme of things, there are very few spacecraft and there are very few rocket launches. So had a bit of a look at so I guess there are different aspects. You've got the raw materials going into the satellites and the rockets, and you've got the emissions from producing those and from the actual the propellant as well. So for production, as a comparison, compared how many cars were sold in 2022 with how many satellites were launched in 2022. So that's the first plot here. You can't see the satellites on the graph because it's a rounding error compared to the number of cars. So in terms of raw materials, there it's not a big impact compared to things like the car industry. In terms of flights, so coming back to yes, a rocket launch emits more than a flight, but last year was the most rocket launches we've ever had in a year, and it was only 182, and I think that was including a few failures, and there are a few failures that were added to that number as well. But 182 launches compared to 31 million commercial passenger aircraft flights in 2022. And so then when you look at the emissions, again, the launch industry emissions you can't even see compared to the road transport emissions and the commercial aviation emissions when we put them on the same graph. So I guess that's to put it into perspective. Having said that, digging into this a little bit further, it seemed that because the numbers are so small compared to other industries, historically there has been a lack of accounting and a lack of regulation around this. And now if you go to the next slide, Rosie, and that has maybe been okay in the past, but we are now getting to a point where we're having a lot more rocket launches each year. So the top graph here is successful orbital rocket launches we've had since 1960. And we've had a big peak in the last couple of years, and we're expecting that to continue to increase. And also massively, the amount of objects we're actually launching into space has grown enormously. So we're looking at nearly 2,500 satellites launched in the last year alone. So yes, maybe it's been okay that we have ignored this in the past, but we don't want to continue to ignore that. So there's kind of a global effort now, particularly led by space agencies, and particularly the European Space Agency, to start having kind of a space industry specific life cycle assessment tool being rolled out, and also looking at how can we minimize the impact of the launches, and also the space satellite re-entry at the end of the lifetime. So if you go to the next the next slide. So this is kind of a system view of what we need to take into account when we're looking at the environmental impact of a space mission. So first of all, you've got a kind of your early design phases where you've got a lot of office work, maybe traveling. Then when you start to build your satellite, you need to build it, and there's also a lot of testing. So assembly, integration, and testing phase, you've got big labs, vacuum chambers, and so on to run. We get to the launch and commissioning phase, which is where you have the launch. Utilization, the main thing there is you need to run your ground stations and your flight operations centers. And finally, we have disposal. So from what I read, the kind of design phase is significant, but the main carbon footprint there is just through running the offices and labs, which presumably can be done with renewable energy, the same as any other industry. So that's kind of low-hanging fruit, I suppose, to deal with. The bigger concerns are the launch part and the disposal part. So the disposal part, we're getting more and more bits of space debris, more and more satellites going up every year. In order to keep low Earth orbit in particular accessible and not have collisions between different satellites and bits of debris, there are regulations around how long your satellite can stay up there after its mission has ended. And so for low Earth orbit, that's 25 years. So you'll generally either, depending on the size of your satellite, have it re-enter and burn up in the atmosphere naturally, or you'll do a final disposal burn at the end of your propulsion maneuver to burn up in the atmosphere. So that's really good from an space debris sustainability perspective, but the burnt up satellites are now in the atmosphere, and the satellites are mainly made up of aluminium, which turns then into aluminium oxide, which has a radiative forcing effect. So that's one aspect that's being considered at the moment. More research is needed to better understand the impact on climate of that. There's still the amount of satellites re-entering, even projected, is a lot less than the amount of just meteorites, for example, that re-enter the Earth's atmosphere, but they are made of different materials, which are potentially more damaging to the atmosphere. And on the other side of that, we have the launch vehicles themselves. So Rosie, if you go to the next slide. So the emissions from your launch really depends what propellant your rocket uses. So this is a breakdown of all the 2022 launches and what propellant they use, and therefore what the exhaust gases were that were emitted into the atmosphere. The numbers don't add up to 180. There are more listed here in the graph than the 182 launches, because you'll often have, for one stage, you might have, for example, hydrogen propellant, but you might also have solid rocket boosters. So one particular launch vehicle might use multiple different propellants for the different stages. The most common one is kerosene. That produces CO2 and other things, but the bigger concern being the soot that's produced, which also has a radiative forcing effect, which isn't particularly well understood in the upper atmosphere, and has been called out as an area that needs a lot more research. Oxygen and hydrogen is really good and also quite common. Only produces water vapor, as well as trace gases of nitrogen oxide when it reacts with the atmosphere. So we really need more of those. Solid propellant, also not good. You have you produce soot, as well as, again, aluminium oxide. And the hypergolic propellants, those are fairly nasty chemicals, at least before they've been combusted, in that they're very difficult to handle. They're highly toxic and carcinogenic. So those are being phased out anyway, but they are still a significant contribution to emissions. Really interesting one is there was one launch last year that used liquid methane and liquid oxygen. That one is a good improvement over kerosene, for example, because you don't have the soot. And it's looking like SpaceX is going to transition more toward that in future, which is largely because of the Mars missions. So methane fuel is one of the things that we can produce in situ on Mars, whether that's from the water ice or from the CO2 in the atmosphere. So that's a kind of cool application, which I think we'll see more of in future, that can potentially be a greener alternative to the kerosene. But otherwise, the liquid hydrogen and liquid oxygen is the way to go. So yeah, there were lots of rabbit holes there, so I'll leave it there. But it's a really interesting topic to dig further into, that I think we're going to see a lot more research coming out in the next few years. You're muted, Rosie. Rosie, you're muted. Nope.
Classic. So I definitely would like to see a video on that topic alone, and largely because it's highly relevant to my personal space travel plans. We have to get this sorted out before I will feel okay to make my space trip, and that's definitely got to happen. So, Cool. All right, we have run out of time, so I'm going to have to wrap up. I mean, like, every topic we talked about today could easily be an hour on its own, and I do hope that I'll get you guys back either together or separately for some more space topics in the future. So I hope that it has been a pleasant experience for you today so that you won't be scared away. So I wanted to mention that I will be I'll be running some panels at the Fully Charged live show that's on in Sydney this weekend, actually. It's coming up this weekend. So anybody who's in Sydney or can get there, if you want to buy tickets, I have a discount code that is in the description. That'll be really cool to see you there. I'll thank once again the sponsor, WeatherGuard Lightning Tech, for sponsoring this live stream, and also mention that they have a great tech newsletter and a podcast that I co-host each week with Alan Hall and Joel Saxon. The links to all of that is in the description. We talk about all kinds of clean energy tech, and in the latest podcast episode, we talked about spiral welded wind turbine towers, which is a pretty cool way to avoid having to transport, huge sections of towers, and will help them continue to grow higher onshore. Check that out on your favorite podcast app, or you can watch it here on YouTube. And I also need to thank once again the Engineering with Rosie Patreon team, who they support the whole channel and help it to grow. And I think the video editing is getting better now that I have got a pro on board. So if you'd like to join us, then there's the link also in the description. And finally, just one more big thank you to you guys for coming. And I have to say, this is probably, or maybe definitely, the most preparation that any of my expert guests have done. It was really cool to see all those charts especially pulled out. It makes it a lot easier to understand what we're talking about. So thanks heaps for sharing your passion and knowledge, and for taking the time to prepare so thoroughly. And I know there's been some comments as well thanking you for spending the time. And so we'll leave it there. But thanks everyone for watching. I'll see you in the next one.
See you.
Thank you.
Thank you. Bye.